So I'm Chris Williams. I'm the LS Randolph Professor of Mechanical Engineering here at Virginia Tech. I also direct my lab, which we call the DREAMS Lab, which is an acronym for Design, Research, and Education for Additive Manufacturing Systems.
That's awesome. That's awesome you were able to make that acronym work.
Yeah, I really promise I did not try to do that. I just sat down in my first year and said, what are the things that we really want to do as a lab? And design is one. We want to talk about how do we design for additive, and we of course want to do materials and process research. And I was also came to Virginia Tech as a half and half appointment between mechanical engineering and engineering education. So teaching people about this new technology, and really there's a big need to get engineers who knew how to use it properly. And so I wrote all these words down, and I spelled this word and said, oh no. So then I went to my first student, who was actually an undergrad volunteer, and I said, okay, our choices are like VTAM lab or dreams. And he goes, just please don't do dreams. And I said, well, I'm going to do it anyways. And then fast forward, this student, my very first student, he's now leading all of materials and manufacturing for one of the naval research centers in Carter Rock. So I get to see him professionally, and I have to remind him, like, see, dreams worked out okay. It worked out for you, worked out for me, And I've only ever received one email asking for a sleep study. So only once have we gotten.
That's phenomenal. I'm glad that worked out for you. I'm glad it caught on, and I hope that you don't get any more sleep study emails. And I mean, unless that's what you want, I don't know.
Right. Yeah.
Well, I know we've talked in the past a little bit about this topic, but I thought a good place to start would simply be, what is additive manufacturing?
Sure. So additive manufacturing is the official standard word that we as engineers use to refer to any technology in which you're creating a part or an object layer by layer, either by depositing material or making material. And the real big word there is additive. And it's to differentiate it from the more traditional ways of making things, where we take a block of wood and we slowly cut away, or metal, we slowly cut away to get to the shape that we want. So that we refer to as subtractive manufacturing. I'm subtracting material to get to the shape I want. Whereas in additive, I'm selectively adding material to build the shape that I want. And that is the official engineering way of referring to what most people refer to as 3D printing.
Okay, so is all 3D printing additive manufacturing? Is all additive manufacturing 3D printing?
Yeah, it's a great, yeah. Again, we're going to use the standard phrase, but yeah, I tend to think of 3D printing more of like the level of like the hobbyist. Like, 3D printers are those things that I can put on my desk, or I can use in my makerspace to make things, prototypes or models or Yoda heads. Whereas additive manufacturing, that's the second key word, is manufacturing. We're very much focused on using these additive techniques to make end use products. I want to be able to take a thing out of the printer and put it directly on my airplane. I want to manufacture final real engineered goods using this layer by layer technique.
Okay, so maybe you could use 3D printing as a part of a larger additive manufacturing plan.
That's fair. Yeah, but yeah.
Okay. Well, that's awesome. Well, what is some of the history of additive manufacturing, 3D printing? When did this kind of start? It seems like it's booming right now from everything I can tell, just in my sphere. But when did it actually kind of begin?
Yeah, 1983 actually is the first commercialization of this idea. So it's been around for 50 years? Or 40, almost 50 years. And so in that regards, even though that seems old, it's still relatively new for manufacturing technology, right? Other manufacturing technologies like cutting away material or casting metal into a sand mold, I mean, those have been around for centuries, right? So although it seems like, wow, 40 years, that's quite a while, it's still pretty nascent. And we have to remember that as a technology, 1983 was sort of the first ever, and it was really focused on quickly making models of things. So we actually, when it was first released to the world, the way I was first introduced to it, which was in the late 90s, we called it rapid prototyping. So it was, how do you rapidly make a model? So if you were a designer and you had a new idea of a shape or something you wanted to try out, you used to have to go to team of experts downstairs, usually downstairs in a machine shop or the prototype studio, and it would take them weeks to just make a model for you then to take a quick look at it and go, oh, that's not right, let me redo it. So the whole idea of this technology originally was, as a designer, I could quickly make a drawing, give it to this computerized platform to make the shape. And in only one day, I would get the shape and I could look at it and go, okay, that's not so right. Let me change it. So I was rapidly prototyping ideas. And then in the sort of thousands, early 2000s, late 90s, we started thinking, well, wait a minute, if we can improve the materials or we can improve the quality of these machines, maybe we could actually use them to make a final product to use. And some of those breakthroughs are much more sophisticated equipment with much more, embedded intelligence, but also the ability to additively manufacture metals directly was a big breakthrough. And that happened around, I think the first one of those machines was like 2005. So those are only 20 years old, really.
So when they made that shift, what was the biggest, I guess, technological change that added to that shift? Was it the materials? Was it the technology? Was it everything?
Man, yeah, it was everything. I think, yeah, people in and that was happening right when I was in graduate school, sort of those early 2000s, where so I got to sort of see it, and it was great because it was a very small sort of international community of researchers, and we would sort of come to the conference and see who had been able to print metal that year, of any quality, and it seemed for a while that it just wasn't quite going to work. And finally, there was a fairly big breakthrough in Germany, I think is sort of the first place where really we saw some really nice breakthroughs where people changing the way in which the laser type they were using, the amount of energy they were using, and the strategies of which to sort of get a part to stay still. I guess is the way to say it. As you print, metal gets really hot and then it gets very cold very fast, and that makes it want to shrink and distort and warp. And we say in 3D printing, the number one rule is that when I print one layer, it has to be there when I come back for the second layer. It can't move, it can't shift. And in the early days of printing metal, that was the hardest part. But if we figured that out, and then now I say about the time I came to Virginia Tech in 2008, that was probably some of the very first days of, you could actually buy a machine that could print a fully dense, like high quality titanium part straight out of a printer using lasers and powdered metal. Again, that's only been around for 15, ish years or 17 years.
Well, that's fascinating. Well, now it seems like that we're able to 3D print in a variety of different materials. I mean, when I think of 3D printing, though, I mostly think of plastic. I will be completely honest with you, or resin or whatever it is. But what are some materials that people that we're able to 3D print with that people may just have no idea? Because I think even for me, just the idea of 3D printing in metal is a little bit of a new concept.
Yeah, I think, well, first let me do a quick side note, which is, when I first started at Virginia Tech, I took it upon myself to be like, well, I care so much about this technology, and I think it could really be a game changer. And so it was sort of like my job is to teach as many students about additive manufacturing as I possibly can so that when they get to their jobs, they can say to their boss, hey, I think we needed one of these machines. And now it's almost like we're at the pendulum has shifted. So it's all about educating people what it is. Now the pendulum has shifted where we have a new problem, which is everyone thinks they know what it is, what it is. So yes, additive manufacturing does involve like a robotic hot glue gun where you're, slowly feeding a stick of plastic and it's melting and it's translating and building a thing layer by layer. But that's actually only one of 7 ways that we talk about additive. So to answer your question, there's lots of different ways to build things layer by layer. Some of them use molten plastic. Some of them are actually using layers to selectively melt plastic or metal. Some of them are curing resins or jetting droplets of glue into powder. In any case, we can now print pretty much any class of materials. We're printing, of course, plastics, but also like carbon fiber or glass fiber composites. We're printing lots of different metal alloys. We're now printing ceramics. We're, of course, printing concrete. And we're even seeing people print, living tissue or tissue scaffolds, soft materials that can hold living cells while you build it layer by layer. And my favorite part about all of this is that you can find all of this here at Virginia Tech. So at Virginia Tech, we have experts across the whole campus who are advancing the state of the art, and we are doing all of those things. We're printing concrete, we're printing metals, we're printing ceramics, we're printing polymers, we're printing living tissue. It's really exciting.
When we go to 3D printing, aside from the speed, which you kind of mentioned before with the prototypes, you could get these prototypes in the early days fast. But aside from the speed, what other advantages are there to manufacturing things this way?
Yeah, actually, should also mention we're printing glass. The architecture, Nathan King is printing some really cool glass. So the thing actually about additive is that speed is actually not necessarily its strong suit. It just depends on how you define speed. if your stopwatch top starts at time from conception to time of first article, it's by far the fastest way. Because traditionally we have to make a mold or we have to make some other components first to even be able to start making the object with the traditional means. But if your stopwatch is, hey, I want to, have 10 million of the same thing and sell them at, a big box store, then this is not the technology for you. So the value of additive in terms of speed is how fast can I make a change and how fast can I get maybe a unique object. And for the first 10,000, this is the faster way. But if I start making more, it's probably faster to go some traditional means. The real value of additive, and that's the one I like the most, is the complexity of shape. So we're able to make things much more complex in their shape than you can make with any other technique. That ability to sort of literally grow apart from the bottom up allows us to selectively place material anywhere we want in space. And then that means we can make shapes that you just can't make any other way. Can't help but just grab something, like this kind of like complex metal lattice structure that I'm holding in my hand. It's a very large object made out of steel, and it looks like almost like a honeycomb. It looks like a truss, a series of trusses. There's no way for me to like use my drill bit and carve out metal and all these complex nooks and crannies. Where with additive, as I'm building up, I can do that quite easily. It's not just shape. So complexity of shape is great for the sake of, I can make a custom fitting object. I can make a knee that fits just my, body. I can make a cast that just fits only my hand. And the time it takes for me to make one for me and one for you is no different. Whereas traditionally manufacturing, I have to make a very custom mold, and then to make one for you, I have to make a whole different mold. So the ability to make complex shapes and change them really rapidly and customize is really exciting. But in this case, I can also make shapes that are very lightweight because I can put material in all of the regions where it's needed, and I can also engineer some unique performance. So this material is really this lattice is very lightweight, but it actually absorbs impact. Well, you can think of in your car, that's how the crumple zone. Well, we can actually engineer this into anything where that impact now makes it fold in certain ways. So basically, with complexity, we get performance benefits. Also, we can think about large systems of parts. You think about, why do we have assembly in the world? All of our things that we have around us are all assembled little versions of smaller parts, and it's because, well, the big thing itself is too complex to make at once. Well, in additive, I can actually combine all those little parts into just one printed object. So we can actually reduce the amount of time it takes to assemble things. And so that's also really great. There's lots of other reasons. I guess maybe one more I'll choose is the idea that and this is the one also I really like, we call it sort of a democratization of manufacturing. So this idea that I have this digital system that I can just give it a digital file and hit a button that says go. A little bit more complex than that, but effectively, right, I can file print is what we always want to do, and I could print a part at my house. It's super local. I'm not relying on a factory, different part in the world. I don't have to rely on shipping. I'm literally shipping only through an email. I can send you a part and you can make it at home yourself. And that has great implications for supply chain management, onshoring manufacturing, but even printing at a camping site, or I'm on Mars, I could actually start making objects I need. FedEx doesn't deliver to Mars, so could I instead have a printer there in the space on the space station, and I can make objects when I need it, where I need it, and I don't have a lot of waste around me. I just I'm only using the material I need.
Yeah,
Clearly, I
that's
can talk forever about this because this is what I love.
no, that's fascinating, and I know that I think you have mentioned before to me that idea of if we possibly go to space, we're on another planet, that could be a critical piece, being able to print a part for some sort of spaceship that maybe breaks down.
Yeah, and it doesn't have to be. We always love to talk about space, but we also, remember the people here on Earth. It also,
Mhm.
again, if a natural disaster comes, if you have electricity, and someone could literally email you a part to make a thing to fix your generator. And of course, I mean, the more, even forget Mars, just during that time of COVID, right? We were having major supply chain breakdowns all over the world. And so to make masks or respirator components, it was impossible to get those made and then shipped. Well, we actually started just emailing each other parts, and now every campus was making components. So we can think about the science future of Mars printing, But the truth is, we've sort of lived the benefits of democratization and ultra local manufacturing here in the New River Valley only 5 years ago.
Yeah, it's probably fun to talk about space, but realistically, what you just mentioned is more practical from and more applicable to my life.
Yeah.
I'm curious what some of the other applications you and your lab are working towards, and specifically, I know that you've been working on, I believe, something related to drones and 3D printing drones, and maybe I'm curious what some of the practical applications might be for something like that.
Yeah. So in our lab, our whole focus is really advancing the state of the art. I still am very partial to, when I came to Virginia Tech, the tagline "Invent the Future," and I hold that close to my heart. So we always like to say in our lab, we're trying to invent the future of additive manufacturing, and that involves changing the machines, changing the materials, changing the way that we design, and just think about the way in which we produce parts. So we have done a lot of projects with drones or quadcopters, not because we're experts in that, but because it's a great case study, a great example of a thing that has benefited so much from the ability to, at a local source, fabricate a complex shape that has to be lightweight and strong and has integrated electronics. And it needs to be a very lightweight but yet very strong material. So we often sort of use a drone as a way to demonstrate some new innovation that we've come up with, right? Some new polymer, or some new print ability. We have actually done a lot of work in like printed circuits, being able to embed circuits and sensors and antenna into objects. So drones are really fun. But one of the things that I think, also we love about them is I had always this dream of, wouldn't it be one day awesome to sort of fabricate an entire machine inside the printer and have that machine like walk out? You just can't help but think about that kind of idea. And so it became then, of course, like, well, wouldn't it be cool if we had a printer that one day could print everything about like a drone, and the drone could just fly straight out of the printer, and then it could just make a whole new drone, and even that next drone could be a completely different shape and size. Well, I guess, goodness, almost 2 years ago or 3 years ago, we actually had a team of seniors in mechanical engineering for their capstone project. I finally said, I think this is the year we can pull this off. We had some really talented students and some new projects out of the lab. And essentially what they created was a robotic arm. Think about like a traditional sort of industry robot arm that's used to like, pick and place things and move things around. And instead of it just having a gripper, we actually added a print head to it. So that robot was able to print the entire drone shape, and then it could go over and pick up motors and electronics and batteries, and then continue printing to sort of encapsulate it all. And at the end of the print, again, no human, we just literally hit go. This whole drone was printed and assembled totally autonomously by a robot, and then the drone lifted off and flew away, and then we were able to print the next one. And so that was really exciting. And that was actually originally motivated by the idea of like, if you're going to go to Mars and, why bring the drone with you? You might want to get there first and figure out what you need. And the weather changes day to day and the payload changes day to day. Or heck, if you're in a natural disaster, maybe today you need to have a reconnaissance mission. So you want to be able to print the drone. You can't wait for the drone to be shipped to you. So print this drone. Maybe tomorrow's to deliver medicine or water or some other kind of payload. So, you could change the design and you didn't need any expertise. You could just have, an operator to literally just hit, download, file, print, and let this thing go to work. And it turned out to be a real thing that we could do at Virginia Tech. It seemed like a piece of science fiction, but it became science fact thanks to the great students here.
Yeah. So how long did it take to print one of those, to print a
So
drone, have it fly away?
we demonstrated two different designs. The fastest design at the time was the whole drone was printed and assembled in 2.5 hours with no human involvement. Right now, we're actually just recently started working on version 2 of this idea, and we think we can get that down to like 30 minutes. So we're really excited about that.
So
Stay tuned for that.
I could put in what I needed in a drone, put on one of the Lord of the Rings, and before it's done, drone's gone.
Absolutely. Yeah, our goal is, especially if it's extended cut, I mean, I think we at least get 5 done with this.
That is phenomenal. That is amazing. And I imagine there's a lot of just applications like you mentioned all over the place for that. Well, are there any other things in your lab? Like what else are you all on the verge of working on, or that you would like for folks to know about right now?
Well, I have too many. It's like picking your favorite child. You can't really have them all. Yeah, I mean, I think we've got some really talented students, undergraduate and graduate at Virginia Tech, who have just done some amazing things. I mean, we are doing everything from developing new machines that can print plastics, the parts that are made of multiple types of plastic throughout the whole thing, so it's stiff and soft or conductive or not conductive. When you look at real objects, it's not just one monolithic material, it's multiple materials all assembled together. So how can you come up with a way to sort of hit go and then the whole object is made? It has shock absorbing and stiff and strong and weak and parts all in one. We're doing a lot of work in large metal parts. How do you make really big parts that could go on a Navy ship? And we're looking at new techniques, some of them invented here in the New River Valley at Meld. In manufacturing, they've come up with a really unique printing process, and we're helping them think about ways to tool path. How do you make really big parts consistently? And the cool thing is we're actually coming up with a way to actually embed sensors into those parts. So imagine being able to make a very large metal part that goes on your truck, and inside that part, it has a sensor that tells you if it's getting too hot, if it's getting too stressed, if it's about to break. So we call it, WISE parts, smart parts. And that's a great collaboration with Hongyu and material science. So we're doing some really cool stuff there. I think the last thing I'll mention, thing that's still really I'm partial to, it's a new actually project that we're starting on behalf of the National Science Foundation, which is, again, going back to those robotic arms, not just to pick and place things, but what we also like about robotic arms is that they can move anywhere in 3D space. Traditional, 3D printing, it sort of moves up and down and left and right and backwards and forwards, whereas a robotic arm can twist and turn, like it has the same dexterity as your human hand. So it maybe gives us more freedom in the way that we deposit the material, such that we can maybe control the way the material is deposited to actually maximize its strength. So if you could tell me up front, like, well, I want a part about this size and I'm going to make it have these kind of stresses and strains, we're actually creating a technique that allows you to deposit the material such that it maximizes its performance. Right now, our early results show that this work is about giving us parts that are 10 times stronger than conventionally printed parts. And that's really just by changing the way, moving from this sort of up, down, left, right only motion, where these layers are stacking, to now actually sort of making it like more like an onion. It has layers all over the place, so they're sort of curving in space, and we're preferentially steering material strength in different orientations. We're getting significant performance improvements. So we really hope that defines a future of additive manufacturing.
Well, not to change too much from looking at the future and all these cool applications, but I'm curious simply, what are some things in everyday life that I'm using, my parents are using, my friends are using, that additive manufacturing is critical to, and I just have no idea?
Yeah, I think the most common one that people are most surprised by, and it's surprising to me because it's been around for almost 25 years now or more, is those clear orthodontics, those braces that everyone uses, right? So those clear braces, you get those every 2 weeks, and they're custom fit just to you. And of course, hundreds of thousands of patients around the world. And if you were to think about that, to make that requires us to you'd have to cut a specific set of custom teeth, to traditionally, subtract material, and it'd be all this wasted material, and it would be so slow. And instead, what that company's been doing for now two plus decades is printing models of your teeth, and then they're forming plastic on top, and then they ship you that plastic. So the thing that's in your mouth is not 3D printed, but the mold that formed that shape, that was printed from based on a scan of your mouth. And in fact, if you have those, you can take them out of your mouth and hold them up to the light, and you can see these very faint lines, and those are the layers from the 3D printed mold. So, I mean, people are literally walking around with parts that were 3D printed or parts from a 3D printed object in their mouth all the time. For any of our older listeners, if you have a custom fitting hearing aid that fits just your ear canal, those hidden hearing aids, every single one of those is printed. So, I mean, there's lots of other sporting goods and things, but those are the two most common consumer products that are printed. But on the other hand, if you've flown in an aircraft in the past 5 years, it has printed components in the engine, in the body. And every time you see a rocket launch from one of these startup companies, their entire rocket motor is printed, because of how complex the shape and how optimized you can make it. So what's interesting about this is that additive manufacturing is offering so much value to people, to companies and their products and the performance of those products, that they're actually keeping it a secret. They don't want you to know. That's their competitive advantage. So the bad news for us as professors is we don't, we have to answer questions like this, and we can't give everything away, but it's it's sort of almost hidden. And in some regards, that's what we've always wanted. I know I'm a unique person. I'm a nerd and I love the way that things are made. So I do go around the world looking at how things are made and like trying to guess. But most people don't care. They just care it works. And at the end of the day, that's all we ever wanted for this technology is for you not to notice it, right? It's just, oh, look at this. It works. It's perfect. It's better than I ever thought it could be. And maybe as a user you don't care how it was made, but that's what we in some regards always wanted out of a technology, right? Maturing is getting it to the point where it wasn't a novelty anymore. It was just a part of everyday manufacturing that made our products and our lives better.
Yeah, so it sounds like I'm already benefiting from additive manufacturing every night with my night guard.
That's right. Yes. Yeah,
And
night
just
guards are going to go a big model for sure.
sleeping right through it, no idea.
No
Which
idea.
makes sense because you're running the Dreams Lab.
That's right.
And there we have it.
Nicely done. Yeah, maybe that does come back to sleep studies in the end. Yeah.